Okay, so yeah, magnetism is typically present in everyday's life. So we have toy trains, compass, or MRI scanners, and more into information technology. For a long time, as storage, we were using magnetic hard drives and are still using them, and more recently, also magnetic random access memory. All of those, or the two of those, have in common that the structures in there are already far below in size 100 nanometers. And so we need maybe a technique to resolve what is happening in them spatially. And in addition to that, what was already nicely introduced, oh, it's not anymore. Can you? Okay, all right, thank you. So we also have more, same IT side, but more going into the direction of data processing or computation. Spin waves, as nicely introduced in the first two talks. And there we also want to go to high frequencies, because that directly scales with the bandwidth of the devices or processing speed. So maybe the aim could be here to approach 100 gigahertz or even higher for other materials. So we need maybe a microscopy technique that is able to simultaneously resolve magnetic, let's say, objects and processes with those resolutions. And if we look at magnetic objects and timescales, as it is randomly put together here in this graph, so spatial axis is going to smaller size in this direction, and here we have, here we have timescales. Yeah. When we look at optical microscopy techniques, then we immediately see that they have really an excellent time resolution, such as MOG or micro BLS or these things, really going down to the femtosecond level. But on spatial scales, they are somewhat limited to the wavelengths of the light. So this is what we maybe can cover. Complementary then for electron microscopy techniques, the spatial resolution is really high, really excellent, but they typically in standard implementation lack a high time resolution. Same is true for surface sensitive scanning probe microscopies. So that leaves actually a certain region here on this schematics uncovered simultaneously. Yeah? And this is where we actually apply soft X-ray microscopy, which in this combined resolution we hopefully can cover the whole range. I will show you how that is technically implemented in my presentation, and I will also show you two examples how we can use that for magnetization dynamics and spin waves, and that is spin waves in ferrimagnets and going into the direction of antiferromagnets, where we can use also magnetic linear dichroism, as I will say later, to be sensitive to the spin axis in the material in a time-resolved way. So, how is this implemented? At first, we need an electron synchrotron, so that's already quite a strong drawback. But I mean, it's possible to always apply for beam time. Everybody can use this tool. It's just that typically we are limited in measurement time. Yeah? So this is the BESI-2 synchrotron in Berlin, where we are operating this microscope. And now what we need for microscopy is, first of all, a monochromatic X-ray beam, because then we can look at the different absorption edges of the materials, say iron and cobalt, where we want to do magnetic imaging in. So in that way, we're also selective to the elements. Then for using X-ray magnetic circular dichroism as a magnetic contrast method, we need circularly polarized X-rays, so that's provided by an undulator, and this monochromatic X-rays are selected by a monochromator device in this beamline here. Then we need spatial resolution that is realized by a diffractive Fresnel zone plate lens, as it is indicated here. Then the X-rays are focused to a single spot, and the sample is then raster scanned through this focal point, and the result in transmission is collected in a single point detector. With that, we can get to a resolution of about 10 nanometers. And then to do that in a time-resolved way, we make use of the inherent time structure of the electrons in the ring. So actually the X-rays come in certain flashes, let's say localized in time. And then we synchronize a pump signal to that, which is typically like a metallic conductor patterned close to our samples, and then we apply electric excitation and we exploit the Ørsted fields. But we could also use other methods that are synchronized to these pump pulses, probe pulses of the synchrotron. Yeah, and then we do like a regular pump and probe method, and those come at a spacing of 2 nanoseconds, but we can interlace our excitation to that we get resolution, at least in special operation mode of the synchrotron, of about 10 picoseconds for periodic processes. So we cannot do single events or non-periodic events because we need to repeat the process many, many times. Yeah, and that given, as I already pointed out, so this tool is actually free to everyone. You just need to write a beam time proposal, and if it's, let's say, granted beam time, then everybody can use it. For our own research, we were looking also into spin waves, as already introduced by Anne Tumak and Ahmad Awad in the first 2 talks in a very nice way. There are fundamental aspects to those, as we have seen yesterday. We can build a Magnon BEC, for example, or it can be condensed. And then with respect to possible applications, there are two main or let's say benefits of using spin waves, and one is power consumption, because there are no electric charges being moved in the propagation of spin waves, and the wavelengths of spin waves are several orders of magnitude shorter than that of electromagnetic waves at the same microwave frequencies. And as it also was already pointed out, we need, in order to maybe apply this one day in technology, we need reliable and efficient ways for generation, manipulation, and detection of spin waves. And in our work, we were focusing on this first aspect here, in particular in combination with miniaturization. So we wanted to address spin waves significantly smaller than, or in wavelength than a micron and possibly 100 nanometers. And in the past, first, just to put this on context one more time. So as already said in the beginning, there are these, let's say, high time resolution techniques based on visible light, BLS, and Kerr microscopy. Then for ultra-short spin waves, one can use also neutrons and resonant inelastic X-ray scattering, but this is not done in a phase-resolved way, and it also doesn't work very well for an intermediate regime, and there we were putting actually this X-ray microscopy. And what we did in the beginning to achieve excitation and detection or imaging of spin waves with sub-100 nanometer wavelengths, we were using such a pair of magnetic vortices in a synthetic antiferromagnet, so 2 ferromagnetic layers. So at first we can image them statically, so you see that there's a vortex in each of the ferromagnetic layers, and also we can resolve the vortex cores pointing perpendicular in the center, and those can now be exploited as sources for spin waves. And this is a time-resolved X-ray image now. So you can see that there are waves excited, and this is at very low frequency, 1 gigahertz. In the center, you see the vortex core, and then waves are propagating. So that is in a way also similar to what our chairman presented yesterday, but these are magnetic vortex cores and not superconducting vortices. And here we reached about, let's say, 100 nanometers, or a little bit below only, whereas, in your presentation, I think you were showing 35 nanometers. But at the time, when this was done, it was one of the early examples of direct, really, imaging of spin waves in phase-resolved way at this wavelength. And a little bit later, we modified this a little bit and introduced anisotropy into the system here, which causes these vortices to be distorted and to form a let's say, localized domain wall. So it's still a vortex, but you have this domain wall. And now, in a similar way as we were using the vortex core before, we can also use the domain wall to excite plane waves now. So this was a circular wavefront. And here we, of course, due to the geometric fact that the wavelengths become, the phase fronts become longer and longer, we lose, of course, amplitude, whereas here it's only the Gilbert damping that causes a loss of amplitude. For these plane waves, we still see in the center the circular effect, but it's damped out more, let's say, faster. And what also could be done was to change the dimensionality of this emission pattern. If we go to very low frequencies, below the gap of these frequencies here, we see that waves are only confined to the domain wall, as it was also predicted a couple of decades ago as Winters magnons, and already about 10 years ago the other two speakers in the session, Aliyev and Awad, identified those waves, I think, by FMR and micromagnetic simulations. Okay, now I told you that we want to also look at ferromagnetic materials. How am I doing with time?
Yeah, that's fine. You still have 8 minutes. So.
Okay, good. So we were looking into a derivative of yttrium iron garnet. So that's doped with gallium yttrium and with gallium, yeah, and was leading to a very low saturation magnetization. These films were also grown by Carsten Dubs from Innovent. And now this is already, let's say, relatively small magnetization, close to compensation. So for normal methods that probe the magnetization, then that would already lead to a small signal. But here we can make use of so-called, let's say, sublattice imaging. So that's an X-ray energy absorption spectrum. So we can actually address the different sublattices separately and get to the full signal still. So let's say we go to this energy with the X-ray microscope, then we can maybe image. Could you? Okay. Now also again like a direct image of a relatively big area of 25 microns. So here's this gallium yttrium film. There's a metallic conductor on top to excite the system, and then you see directly in the direct view of that waves being excited at the strip line. So I should mention now this is also has a perpendicular magnetic anisotropy and is forced now to be in the film plane with a relatively strong, or for us strong, magnetic field. Now we can go also to a normalized view by just dividing each frame of this image by the average, meaning that we are only sensitive to magnetic changes or oscillations in the sample. So then you really see very nicely now those waves propagating. And what we found here was that actually there's a nonlinear excitation process going on. So for small excitation amplitudes, we see a very mild signal only, or say precession angles of about 1 degree. But here, in this case, since this is XMCD is also a quantitative method, we can really say the angles here in the center are about 25 degrees of deviation into either direction. Yeah, so that's a really super high amplitude excitation that we can observe here. And I think that we see that those waves are propagating over far distance, although the CIRC has been strongly modified. I think is in line what we have seen yesterday in the talk by Kristina Levchenko on the FMR results of gallium yttrium, that the damping is still quite good in this material. We can also look at domain dynamics in the same film. If we apply smaller fields, then the magnetization is inclined, and then you can really see also then kind of inclined domains are forming, and you can make them, if you want, to dense at 118 megahertz excitation frequency or lower excitation frequency. And in a normalized view, this would look like that here. And in a different sample that has a little bit higher magnetization, effective magnetization, we have domains to be formed, even at zero field. So this is a zero field image here at, again, lower frequency, 70 megahertz, and then you have these stripe domains. And yeah, thanks to this low damping, you can also see very nice, yeah, if you want to say, confined waves to the domain walls, or it's just a mode of dynamics of the domain. And in the same materials, if the correct fields are applied, you can also form such a bubble or skyrmion bubble crystal here and also excite that. And as the last example, so this was all using X-ray magnetic circular dichroism, so that's probing the magnetization. We can also try to use linear dichroism to probe antiferromagnetic materials which don't have any net magnetization. That would lead to the field of terahertz magnonics, so that could also mean much faster processing speeds if it's applied, and at the same time antiferromagnets are very insusceptible to external magnetic fields, which can be good for memory devices, or can also be a draw. But now the example that I show you is not directly on a true antiferromagnet, but just shows the possibility of the technique. So we use again just normal YIG, which also together with XMCD shows an XMLD effect that is quite strong. But first I show you the XMCD. So we were making a lamella out of a piece of YIG, and it was forming such kind of multi-domain vortex states again. So this is, we can probe this by tilting the sample. You see this Landau state, and if it's mounted in normal incidence to the X-ray beam, we can again, as in the beginning, directly resolve the vortex core here in the center, here in normalized view, and there's a gyration of this. Again, very low frequency, 70 megahertz. So that's far away from terahertz, but still. And then, similar to the spectrum I've shown you before, there's now, when we use linearly polarized light, then there is a difference depending on the spin axis in the sample, how that projects onto the linear axis of the light, and there we have an XMLD effect over energy, and we can go to this point here and now directly image using time-resolved XMLD imaging the domain dynamics here. We cannot anymore distinguish between the orientation of those domains, but okay, for an antiferromagnet this would not exist at all, but it's just proof of principle showing the imaging capabilities. Of course, yeah, this is far away from terahertz, and we are still a little bit limited with this 10 picosecond resolution to a certain class of antiferromagnets, but it can go into the right direction, and it might be improved in the future. So in summary, I've showed you that X-ray microscopy can be used to image magnetization dynamics and spin waves with this combined resolution using XMCD. We can use it for imaging of ferrimagnets with very strong signals still. There's this high amplitude spin wave excitation, domain dynamics, and also we can cover a really wide range of frequencies right now. And XMLD imaging could be used for time-resolved imaging of antiferromagnets. Yeah, I would like to thank in particular those people here. So Sina Meyer, she's a PhD student in our group, and she was performing this excellent work here on this gallium YIG mainly. Joe Bailey was doing the time-resolved XMLD imaging, and Markus Weigand was building actually the microscope and is keeping it in shape. And of course, the others also I would like to acknowledge. And you for your attention. Thank you.
Yeah. Thank you very much, Sebastian, for your nice presentation. And
thank you. You have always the best experimental results. It's really impressive, this especially gallium YIG for me personally. It's so nice phase profile and so on. But my question is about, so next step will be full compensation, yeah? Completely antiferromagnetic. So you said that this linear dichroism should be able to see this fully compensated gallium YIG. Is it correct?
Yes. Actually, for the fully compensated gallium YIG, we can still use XMCD because we can address the different sublattices separately. Because, I mean, there's a small chemical environment difference of the atoms in the tetraheders and octaheders, and so that we can separate. But for something like nickel oxide or what we are looking at, hematite, there we cannot do this. So there we can only use LD, and that is what we are doing.
Yes, and then following question, but how about frequency? Because you said that potentially you would like to go to terahertz, and then at the conclusion slide there was 30 gigahertz.
Yeah, true. So terahertz we cannot do at the moment. So there was the plan by Bessie to introduce like a hybrid operation mode where you would have very short X-ray pulses of 1 picosecond together with, let's say, the normally used X-rays for all the other experiments. Unfortunately, this project was shifted to 2027 or something like that. But I would say now we could go up in ideal case to 100 gigahertz, but not to a terahertz right now. Yeah.
Cool. Thank you very much.
Yeah, there are a few more questions from the auditorium. So.
Thank you for the very nice talk. I have two questions. One is, what is the thickness of the materials that you were showing, so this gallium doped YIG? And the second one is for the bubble-like domains that you were showing. Could you elaborate a bit more what you did see with these bubbles?
Okay, first question. Yeah, I didn't mention. So it's a transmission technique for soft X-rays, and that's actually also quite a big drawback because we are limited to order of magnitude 100 nanometers in thickness. I mean, sometimes we can go to a micrometer, but 100 nanometers. So those films were in this range between maybe 100 and 200 nanometers. So what we need to do for this YIG samples that need to be grown on GGG to be perfect, then we need to thin down the samples and like by grinding and by focused ion beam to make a window from the back. So that's actually quite an effort to do that. For the bubbles, I am afraid I don't have the material here with me. I mean, you see kind of gyrate what we saw. I mean, we didn't see all eigenmodes that are probably there. We also didn't look for them, but kind of a gyration. I think that is what we saw.
But would you be able to do with very thin ones? So let's say I was not afraid of being thick and etch the substrate and so on. So imagine that you can do this in the best situation. So how thin could be the films that you could image?
How thin, you mean? Okay. There's no strict answer to that. So I would say of the order of 10 nanometers, maybe 1 nanometers, we could still see, because for the bubbles, you would have a gigantic contrast. It's always 180 degrees in magnetization if it gyrates. For the spin waves, 1 degree, then the signal might be smaller. Yeah.
Thank you.
So we have a further question from the digital auditorium. So from Alexander Srigaflis first.
Thank you for a nice presentation. Here it is. I would like to ask what do you think? If it would be possible using your technique to see parametrically excited spin waves?
Yeah, this we did. This should work. I mean, what we observed there, that sometimes there's a phase ambiguity of 180 degrees. So we saw kind of a flickering sometimes that they would go in this phase or the other, but it's definitely possible to see parametric excitation if it's coherent or, let's say, phase stable to the excitation.
Okay, but also the development of this question, if we have some system with condensation of magnons, would it be possible to see spontaneously condensed magnons if phase will be locked? Or this spontaneously
if you can really lock the phase, then we could see it. If it doesn't lock to a phase, then we wouldn't see it in the standard implementations. I mean, there are ways to think of maybe how to get to a point that one could also, once the process is started, let's say that we can just measure the times of when photons arrive. But in the standard implementation, it's not possible without phase logging.
Okay, so thank you. Thank you.
Sebastian, may I ask also a question? Sebastian?
Yes.
Yes. You mentioned that you are able to distinguish layer by layer antiferromagnets. Surface of antiferromagnet supposed to be different from the next layers. Are you capable to distinguish even on this level the difference between surface and the next layers?
Okay, I'm not sure. So what I've shown was this synthetic antiferromagnet for different materials. If there's a, let's say, substantial energy shift for the XMCD effect between the surface and the bulk, that could be possible. Otherwise, one can also use a technique that is called total electron yield imaging, so that we just measure the electrons that would be, or the current from the electrons that are emitted from the surface, and with that one is limited to imaging the surface. However, we haven't implemented that for time resolution yet.
Yeah, Sebastian, very nice experiment. So for the gallium Yig with this metallic line, so there you have basically the metal is like normal metal. It's not like a spin hole or.
No, it's just using the Ørsted field. It's just, I think, copper we used at the time.
Yeah.
There's no reason why, I mean, one could also use spin hole maybe, but I don't know if that's more efficient because the film was so thick, like 200 nanometers. But in principle, it should be possible, but we didn't do it.
Yeah, but you can do it in the case that you form something that is lockable to your.
Yeah, exactly. So
yeah, okay.
if something is lockable, then it should be possible. Yeah, then definitely.
But yeah, and the second question regarding this, like the shape. So you see that the pattern is basically on one side of this like narrow region of the metal. Is some? This is due to variation of the metallic.
I'm not sure. So it could be a variation of the electrode. It could be a variation of the film. It could be a variation of the thickness of the GGGs that is still be. So there we actually have some 100 nanometer variation of the thickness of GGG behind it, and that could lead to a different temperature locally. So and since this, so we actually went to an excitation amplitude that was just when this process, this nonlinear process kicked in. So it's just a tiny difference, and then in excitation amplitude, and then you would have it everywhere. It was just for visualization that you have this small source that we went to there. But I don't know what actually is the reason why there's a small variation.